So, talk about the homework first. So, good job on the homework. Basically doing binary to decimal conversion and back, and doing some arithmetic and dealing with 2's complement, negative numbers. So, things to watch out for on there. Number one, make sure you're using 8 bits. Okay, it's really important, especially when you have negatives involved, that you do everything with 8 bits. If you truncate it just to where the last one is, sometimes you'll end up getting the wrong answer when you deal with 2's complement and stuff. So even if it's the number 3, write it out like this. If we're saying do 8 bits, write it out like that. All right, even with all the annoying zeros in the front. On question 3, I wanted you to convert the answer back into decimal, right? And some people didn't do that. They left the answer in binary. Make sure that you convert it back into decimal. So if your answer, for example, for 3A was this, how do you convert that into decimal? This is 1, 2, 4, 8, 16, 32, 64, 128. You find all your ones. This is 64 plus 32 plus 4 plus 2. That's 102. And if you got any doubt about how to do that, make sure you show some sort of work, so I can know if you just guessed and got the wrong guess, or if you actually did this and you just added wrong. If your answer comes out with a 1 in the front, for example for 3C, this was the final answer that you got and you want to convert that to decimal, you can't just add up powers of 2 because you'll get 200 and something. So you note that this is a 1, take the 2's complement, so invert and add 1. And then do, 1 plus 4. This is the number 5. Since we took the 2's complement and we got the number 5, our original number must be equal to negative 5. Okay, so that's how you can convert something to decimal if it starts with a 1. If we're doing 2's complement, we're almost always dealing with 2's complement, which is just a convention which says if we want to represent an integer less than 0, toggle the bits, add 1. Make sure you put your first name, last name, full names, no initials on the homework upper left corner, and make sure you staple your pages together. There's a stapler in here. There's also a stapler at the front desk where Angela sits, and either one of those works. So just details. Other than that, the homework's looking beautiful as far as organization and use of the page and so on and so forth, so keep that up. And I looked at all 3 questions, even though I said I'd only look at 1. I looked at all 3, so conversion from binary to hex looked good. The A through F are just something you have to sort of memorize and get used to, make a table or something like that. So this one in particular, right, this is the number 3. This is the number 12, which is C. So 10 is the first one we can't do anything with. So 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, 15 is F. And 15 is the largest we can get. That's your 4 ones. So this was FF, hex. And then the other one was 95, and those are both just 4-bit binary numbers between 0 and 9. So any questions on that homework that you just got back? If I put a note on there like ask about this or something like that, it means that maybe your answers were further off, or I couldn't understand exactly what you were doing. So make sure that you understand converting between binary and decimal and other bases like hex, and doing this addition and then dealing with negatives. And if you got questions, go ahead and ask or catch me in office or something. Okay, so homework 3. as I said, I intended you to have a week on it so you could come in today and ask questions about it. If you already got it done, if you want to turn it in, I'll give you 20% bonus on it. So you get 12 out of 10, highest score possible. If you want to do that, go ahead and turn it in now. If you want to turn it in on Thursday, that's what I actually meant the due date to be. So I haven't changed it in Canvas, but I'll take it Thursday without penalty. All right, so questions about the homework. Yeah.
I was a little confused between the max term. I figured what the midterm was, but max term kind of still iffy about.
Okay. Let's make up a problem. So I'm going to make this easy on myself and not have too many zeros in there. So this is our function f of a, b, c, d. Is that easier to read? So max terms, right, we just start from 0. This is max term 0, 1, 2, 3, 14, 15. Uppercase M's. So if we want to write f in terms of these max terms, find all the places where there's a 0. So M3, M6, M7, and M10, and just AND those together. So that's a max term representation of f. That's a compact form. Now if we want to write this as an explicit product of sums, you have to spell out what each of these max terms are. So to write M3, we're going to write some combination of A's and B's and C's and D's, possibly with bars on top. And it's the opposite of what we do with min terms. So if we have a 0 for A, we're just going to write A. 0 for B, we're going to write B. A 1 for C, there we're going to write a C bar. And a 1 for D, we're going to write D bar. So with min terms, we write A bar for 0 and A for 1. For max terms, it's the opposite. If it's a 0, it's the variable. If it's a 1, it's complemented. And then we're going to OR those together. So these are sum terms. For M6, A, B bar, C bar, D. And those get multiplied together. M7, A, B bar, C bar, D bar. And then M10, A bar, B, C bar, D. So there's the full representation of F. And if you want the super compact form, we can write that. And it just means it's the product of those 4 max terms. To help? Okay. You want to do a K-map for this one? Why not? All right, so K-map for a product of sums, we fill in the zeros. So 0, 0, let me put these in first. So we fill in the zeros, so 0, 0, 1, 1 is right here. 0, 1, 1, 0, and 1, 1. 1, 0, 1, 0 is right there. And I wanted that to work out nicer. Why didn't that work out? 1, 0, 1, 0. Okay, my bad. And then we cover this. So that's one rectangle. That's a second rectangle. And this one, the only thing we can do is a 1 by 1 rectangle. And then look for the variables that change or stay the same. So A has got to be a 0. So for a 0, we write the variable without a bar. B changes. C is a 1. So we write that with a bar. And D is a 1. So we write that with a bar. So there's a sum term corresponding to that rectangle. This sideways rectangle, A has got to be a 0. B has got to be a 1. C has also got to be a 1. It's a 1 there, it's a 1 there. And D could be a 1 or a 0, so we ignore D. And then this lower rectangle, this is just going to be one of our max terms. So A is a 1, B is a 0, C is a 1, and D is a 0. And so F is just the product of these three things, which is a fair bit simpler than the product of those four things. But A bar B, C bar D, that's this term down here. Right, so presumably this times this is equal to the product of those first three. So it's a simplified version. All right, other questions on homework? Or, yeah, on homework? I hope I didn't use the same function. No, I didn't. Good. All right, how's the lab going? How did the lab go? Yeah? Cool.
It's hard to put the payout. It's pretty cool.
Excellent. So I did change your lab dates. So I was going to go over lab 3 today and make it due a week from today, but I've decided you're not going to have a lab this week, so I'm going to push it back. So lab 3 will be due on May 7th, and we'll go over it either Thursday or next Tuesday. The reason being, I want to make sure we have time to catch up on sum of products, product of sums, and the stuff that you're going to need for lab 3 is probably going to take more than just today to go over. So I want to have plenty of time to do that, maybe to do some homework related to it, and then let you start lab 3 fully exposed to everything that you need for that. Because lab 3, the big part of it is basically dealing with binary addition. You're going to build circuitry to make an adder, which is pretty fun because you can toggle in some binary numbers and it'll show you what the sum is. We're going to have to figure out some pieces first to make that happen. So I had left a lot of room in the schedule. So after lab 3, right, lab 3 will be the 7th, next lab a week later, next lab a week later, next lab a week later, and then there's an extra space Actually, it's just one more week to lab 7, and then we're done. So this will be a break from labs. And I'll post new homework.
Total of 7 labs?
Total of 7 labs, right?
That's total?
Sorry?
Just in total?
Yeah. I may make an optional lab 8 for like extra credit. I haven't decided yet. I have an 8th lab, but it's not going to be mandatory. But I might make it available. All right, so you ready to move on? All right, so we can write sum of products, we can write product of sums. We talked about XORs, right? If you're doing a K-map and you have a checkerboard, a sum of products, product of sums is going to be annoying. It's just going to look like the plain old unsimplified expression, because if you have checkerboard, each rectangle is isolated. It's a 1 by 1 rectangle. So you may use XORs. And I mentioned XORs come up when we do addition, when we build adder circuits. So let's talk about how we do addition in binary. In your homework, you did something like this. There's 2 numbers we want to add. And you added these 2 numbers. 1 plus 1 is 0 with a carry. 1 plus 0 is 1 with a carry of 0. 0 plus 0 plus 1 is 1 with a carry of 1, carry of 0. 0 plus 1 plus 0 is 1 with a carry of 0. And our original carry here was assumed to be a 0, right? There was nothing to carry over. So this was really just 0 plus 1 plus 1. So this is 9 plus 5 equals 14. So math works. So let's think about 2-bit addition. Yes?
Can you subtract binary?
Yeah, you can add the 2's complement of something.
Like, instead of just a plus, you use a minus.
So you can do 2 things. You can subtract, right? So if we want to do 9 minus 5, 1 minus 1 is 0, 0 minus 0 is 0. 0 minus 1 is 1 with a borrow of 1, right? And then 1 borrow the 1 is a 0 minus 0 is 0, so 9 minus 5 is 4. But subtraction feels harder to me, right? It felt harder in school. You can build a circuit to do this pretty easily. But the alternative, this is positive 5. This is negative 5, 2's complement. And if you do 1, 0, 0, 1, and you add negative 5, 1 and 1 is 0, 1, 0, 1 is 0, carry the 1, there's a 1, 0, 1, 1 is 0, with an extra 1 at the end. That's 9 minus 5 is 4. So oftentimes when we want to take A minus B, what we do is we convert minus B, we convert B to minus B by taking the 2's complement, and then we add it to A. So it's still just a single addition circuit. We just need a way to take the 2's complement, and we'll see how to do that in a bit. Let's think about 2-bit addition. And let's forget about 2's complement for a moment. Let's just go back to plain old 0, 1, 2, 3. Those are our only numbers. And if you do something like 0, 1 plus 1, 0, that's 1 plus 2, that gives you 3. And if you do 2 plus 3, that gives you 5. And if you do 3 plus 3, that gives you 6. So it looks like we need at most 3 bits of output, right? If our sum is just 3, as 3 bits, that's 0, 1, 1. But the biggest numbers we could possibly add would be 3 plus 3. The biggest sum we're going to get is 6. And 6 fits in 3 bits. In fact, there's nothing that'll ever add up to 7, but that's okay. So first, let's design a circuit for doing binary addition. And this is going to be fairly ugly, and then we're going to look at a better way to do this. But in your lab, you're going to have to do it this long way first. And then you're going to get to actually implement it with the easier way. But I want to make sure that we believe this longer way first. So first step in designing a circuit is make a system diagram. So a view of the circuit without concern for how we implement it, but what does it do? It allows us to input two 2-bit numbers, so I'm going to call this a 2-bit adder. And we're going to put in two numbers, A and B, and I'm going to label them as follows: A0, A1, B0, B1. And it's going to produce a 3-bit sum, which I'm going to label these bits S0, S1, and S2. Now that's a good start, but that's not sufficient. If we wanted to build a computer and use this as part of our add circuit, we don't know enough to know how to hook this thing into anything else. Because we don't know what A0, A1, B0, B1, S0, S1, and S2 are. We could make some guesses, but you don't want to guess when you're building circuitry. Because you guess wrong, it bursts into flames and the universe explodes. So we want to understand exactly what these inputs and outputs are. So I would write a description of this something like this: S equals A plus B. This is addition, not a logical OR. And S is a set of 3 bits, S2, S1, S0. I could also have said S0 equals the least significant bit, and S2 is the most significant bit. Or I can just write it down like what these look like side by side. I'm going to do the same thing for A. The number A which is being added is A1 followed by A0, and the number B is B1 followed by B0. And if I went with this language, I would write something like this. These are the kinds of details that make the difference between mission success and disaster sometimes. Right, so you know all the famous videos you can find online of rocket launches going bad, right? Things exploding on the launch pad, space telescope that can't focus, the first version because there was a units mix-up, details like that, right? So you really want to be absolutely clear to whoever is reading this what each of those inputs and outputs are and what this block does. It adds A and B, it produces a sum which is called S, and that's what those bits are that make up A, B, and S. So that's your first step in designing something, is make a good system diagram, label the inputs and outputs, describe the behavior. The next step is to figure out what goes inside here. What do these get connected to? What do those get connected to so that this performs this operation? So what's the first step of coming up with that design? Say again? Truth table, exactly. So write a truth table because that's a way to describe outputs in response to inputs. So keep this somewhere handy. And let's write a truth table. So what are the inputs to your truth table? They're the inputs to your circuit. So I'm going to write these down: A0, A1, B0, B1. And what are the outputs? They're the outputs from the circuit. So S2, S1, S0. This is a pretty big truth table. It's got 4 inputs. How many rows do we have? 16. I'm going to make a rubber stamp that just like prints out the left side of a truth table. That must exist. I'm gonna make one anyway. I'm gonna give it to Izad. He'll like it. All right, now we need to fill in the outputs here. And this takes a little bit of work, because there's a lot of ways to do this, and only some of them are actually gonna be correct. So remember, we're taking the number A and we're adding the number B. Well, this first row is pretty straightforward. The number A is 0, 0. The number B is 0, 0. When I add those together, I get 0, 0, 0. So that's what my output is. Okay, let's just come down here to the 7th row. The number A is 1, 1. The number B is 0, 1. When I add those together, 1 and 1 is 0 with a carry, 1 and 1 is 0 with a carry, and a 1, the output should be 1, 0, 0. Got the idea? All right, so I want you to go to the board and, working as neatly as you can, come up with the full truth table for this 2-bit adder. And do this in whatever size groups you want, but make sure everybody gets a turn on filling in some of these outputs. Okay, don't just have one person doing it and others watching. And then we're going to go ahead and come up with equations from there. Yeah?
Just like, is it you just like taking the swap input the A and swap input the B and add them together to and throwing out the previous?
Exactly, yeah. You just have to do that 14 more times. And I suggest you put these things in the same order, because I'm going to write down our consensus answer here.
B1, B0, A1, A0.
It goes B1, it goes B1.
Yeah, I realized I have to make it very, very simple. Oh, yeah.
We're not saying what it says, we're just what should be on there. So these ones are easy.
And that's when it
Just a black pen.
that's good. Now, if you don't have the line,
52, 1, 1, 2, 4, 9.
No. Oh, shoot, I'm sorry, I was doing it. This other. Wait, what? I was doing it down.
Yeah, and then we can have a weird line. Oh, yeah, you're right. There. Uh-oh. We missed some one. You forgot it's 0, 0. Hi. Oh, this is not here. This doesn't. So then this line actually needs to go.
Yeah, I'll put 3P because I think
There's the 3 and 511.
101. That needs to be 10.
Oh, yeah, there's,
So then this line needs to be higher. No, that should be 0. 1011. And then no, you're right. You're right. He fixed it. Okay, so then draw this line. Sweet. And then 1 0 0 0. 1 1 0 0. Cool. 1 1 0 1.
I was like, wait a minute. It's not adding enough.
So that's 0 1 1, right? And then
So basically, silly humans.
the one that is 1 1 1.
No, it should be
1 0 1. Oh, right. So the one, yeah, you're right. You want to write that one so that we make sure that everybody's.
All right, so if you finish this,
1 0 0.
start trying to write equations for S0, S1, and S2.
This one actually
Came out.
1 0 1, right?
Oh, no, we can't. Because it's.
1 0 1.
You could.
And that's 1 1. That's 1 0 0. No, 1 0 1.
Why do we
Yeah.
from 11 to 9?
Well, let's just use
That one's 1 0 1, right?
No,
Oh, yeah, you're right. You're right. You're right. So they're doing.
That was perfect.
this one should be.
Cayman.
Oh, no, yeah.
You got your thumbs up?
Yeah, that's
Cool.
good. Perfect.
Sweet.
So I'm supposed to do that was supposed to do it?
Yeah, let's do it. Why not?
I was thinking what else is doing it.
It makes sense.
Wait, would you have to make 3K maps then? For each? Yeah, you have to make 3K maps. Okay, I'll set one on each side of each.
So that's, we're going to call this B1, B0. Oh, no, you're right. You're right. No, you're right there. And so you're making B this side? 0. 0. Oh, right. How did I forget this? 0 0 0 1 1 1 1 0 0 0 1 1.
I know we gotta do that.
So then 0 0. So then,
this would be the S plus S2.
so then okay, we'll call that S2. Do you want to fill this out and I'll make another K map?
Alright, so which one are you doing? Am I going to do S0?
Do S0 and I can do S1. We're making A's on top. Okay, cool. Confusing. Okay. 0, 0,
Because we need.
Yeah, okay, so now we're doing this one, so 0, 0. I'll do this, I'll do this. What is it?
You can't do it. Yeah, it was 1, 2, and 1.
Oh, fine. Yeah.
And that makes sense.
Two products of some or something.
At this point, I'm very confused.
What are you confused by?
Are we doing some products for this one, for the came out, or a product of some?
Up to you.
We go either or.
Yeah, most people are probably doing some of products.
Okay.
No, because that one would go here. Yeah. So this one would have to go there, which is like diagonal. So you can't hit it.
Up and down, you're right, you're right.
Already got it.
And then that'd be I think technically it's
I got to pull this over. To which you can make them into fours. Into 2 by 2s. Then you just make a box.
Part of these.
And then you just do this each one specifically, but okay, what change what change? So one B0 change is the same as B1. And then the B1 change so the other one, A1 is the same. So this one for the big is just
Here?
B1, A1.
Am I doing this K-map right? I'm forgetting. So A1, 1, 1, that changes, so there's no A0, 0, 0, so not B1, not B0? For this.
For that one specifically?
Yeah.
That should be. There's these two. The B1, yeah. And then A1 is the only one that changes. Yeah. You're doing, this is product of sum. We're doing, because this is, you have written out for sum of product. Because sum of products, you make everything, you want everything to be one. Right. And then, but we have the ors between all of them. So when you were doing sum of products, you're adding like all of the different possibilities together. So for this one, to do this would be the opposite. This would be sum of product, the way you did it.
Okay,
So
so
to do
I'm
that-
doing everything zeros.
Yeah, because if you want to use the,
That's what I wanted to make
if you want to make this is the stuff that we learned
Right.
recently. So yeah, if this is how you want to do it, then this would be the correct way.
Okay.
Because you want everything to be zeros, and then this would just be one thing, and then this would be multiplied with the next.
The next line.
Yeah. But if you want to do sum of products, then you would do it like this.
And a quick check you can do, count up the number of ones and compare it to the truth table, just to make sure you didn't miss any.
Okay. Are we supposed to have 3 different truth tables?
Yes, you're gonna end up with 3 because you got 3
I am missing one.
equations.
Okay.
1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7.
Do you want to read them off to me and I'll see what I missed?
0, 0, 0. You have 0, 0, 1, 0. 0, 0, 1, 0, and you have 0, 0, and 0, 0, 1, 1. Just that.
0, 1, 1, 0? Yes. Okay.
Yep.
Okay, so I guess this forms from
Yeah, that was the only one you made. But yeah, that's how you do for those things. Because this is product of sums, and what I did is sum of products.
Which one would you prefer? Does it matter?
He said you can just choose whichever.
I'll do your way, actually.
Oh wait, I just realized too, that's not how you would be doing it too for product of sums. Because when you're doing product of sums, you're looking at the zeros.
Right, instead of 1.
Yeah, and so it would, yeah.
So you want not A1.
Because you want everything to be, one, and then you don't do, and you just put them right next to each other.
B1, B0. B, and then the not of those. And then or right? With all the rest of them?
Yeah, pretty much.
Cool.
Yeah, the other one is kind of confusing because you have to use all the zeros.
Those, I don't
I got it right.
Yeah, they would all be in the same area, it would just be
There's so many.
that. Be like that. You do like B1A0 and then A1B0, that would be different.
No, I was thinking like up here, and then here.
You know?
Yeah, I know.
I thought that was a quick one, it looks a lot. Or like, we started doing the K-notes and I was like, you were doing this wrong? I don't have to worry about it.
Every Chromebook I've touched has a job.
I'm probably gonna right? Good.
Good.
Like a Dell. So pretty good. All right, so everybody's got good K-maps drawn, everybody's got good covers of the rectangles, and some people are finishing up the equations. So if you want to take a short break, or if you want to finish up your equations or whatever, let's come back at 1 o'clock, and then we'll talk about this, and then we'll talk about a second approach to doing this that takes a little less work.
Okay, so a question kind of crossed my mind the other day.
Okay.
It's like, is there like an advantage to using a sum of products over product of sums?
It's hard to say. Sometimes one will be significantly easier than the others. If you have a lot of zeros in your truth table, sum of products is probably going to be cheaper because you only need to write down terms for the ones. But if you have, 14 ones and 2 zeros, product of sums is only going to have 2 sum terms.
Oh, okay.
Right. So that's one version. If you simplify your equations, you're often going to end up at the same place, though. So it kind of depends.
All right.
Mostly in this course, you're told, do sum of products, do product of sums.
Alright.
That's the big difference.
Okay.
Yeah, good question.
Ooh, so many numbers.